Due to their capabilities, field programmable gate arrays can be used to create hardware-software platforms that keep their flexibility at runtime, allowing the development of different kinds of reconfigurable computing systems. This scenario leads to a context where this system can be in the form of programmable system on chip, programmable system on multiple chips, or, generally speaking, heterogeneous computing systems. Modern FPGAs are no longer just a bunch of reconfigurable elements. They can contain DSPs, reconfigurable elements, and general-purpose processor, which can be both physical CPUs embedded in the FPGA fabric or soft cores mapped on a part of the FPGA. On one hand, the heterogeneous nature of a programmable system on chip, characterized by the coexistence of both software executed on at least one GPP and the hardware implemented on the reconfigurable logic elements, can be found back in the years in Xilinx Virtex-2 Pro devices, where an IBM PowerPC 405 was embedded in the FPGA fabric. Since then, a lot has been done. An example of this is the Xilinx Zing 7000 all-programmable SoC family, which integrates the software programmability of an ARM-based processor with the hardware programmability of an FPGA, enabling key analytics and hardware acceleration while integrating CPU, DSP, and mixed signal functionality on a single device. Built on the success of the Zing 7000 all-programmable SoC family, Xilinx designed the ultra-scale MP-SoCs architecture. Another example is the ultra-scale multiprocessor system on chip, or MP-SoC, which extends the Xilinx system on chip to enable true heterogeneous multiprocessing with the idea of being able to implement the right engines for the right task, to implement smarter systems. Furthermore, the ultra-scale MP-SoCs architecture provides multiple advanced processors that scale from 32 to 64 bits with support for virtualization. On the other hand, in terms of soft cores, Xilinx provides the Microblaze and the Picoblaze soft core processor to be used in a system implemented within their FPGAs. The Leon project was an initiative by the European Space Agency in late 1997 to study and develop a high-performance processor to be used in the European space projects. The objectives for the project were to provide an open, portable, and non-proprietary processor design capable of meeting future requirements for performance, software compatibility, and system cost. There are also other FPGA companies, but Xilinx, who design their own soft cores. This is the case of the Nios 2 processor designed by Altera and of the LM32, which is a configurable soft core specifically optimized for lattice semiconductor FPGA devices. A lot has been also done around the RISC architecture. The Open RISC 1000 architecture has been started from an initiative to develop a freely available RISC architecture. For the first few years, the project was backed by their employer, Flextronics, who produced an ASIC version of the design. Since the very beginning, the project was led by an independent community, opencourse.org. While opencourse.org hosts over 1,000 projects today, the Open RISC 1000 remains its flagship project. RISC processor designs, labeled as such, date back to the early 1980s and have always been of academic interest. Academics created the original RISC instruction set, DLX, for use in the first edition of the Hennessy and Patterson textbooks, Computer Architecture, a Quantitative Approach, in 1990. However, this instruction set architecture was intended primarily for educational use. The RISC-V instruction set architecture is the fifth generation of this original work, and it's quite suitable in both commercial and academic environments.